Okay, all right, guys. Good evening. And okay, all right. I guess we should start. There are only three people right now. There were a few more, but I guess they got scared due to less attendance. But all right. I hope all of you are doing well, and I think we should start. Okay. All right. Is my screen visible to all of you, and am I audible? Yes. Okay, I am. And my screen is also visible. Okay. All right. So good evening, everyone, and welcome to the last session, session number 4 of Gemini Study Jams. Okay, all right. So this session is about. So of course, I'll first of all let's recap what we did. So we covered a variety of topics in Gemini Study Jams. First class was about what is fine tuning and how do we actually do it, right? So then the second session we took was about how to specifically do perimeter efficient fine tuning using LoRa. So we looked into that. We did some fine tuning, we saw some code, and we did that. And in the third session, we continued that with a more theoretical perspective as to what exactly we are doing in the architecture of the transformer, what we are actually changing. And we covered a variety of topics. And so this session is about model performance and deployment. So I have some good news for you and I have some bad news for you. So first of all, let's go with the bad news. The bad news is that I'm not an expert in MLOps, right? I don't know MLOps as well as I could explain to you the theoretical concepts. And the good news is there is some other things that I know in its place that we can look at in this session. So rest assured, you will also learn something today. And first of all, let me just set the tone of the session. So in the previous sessions, we tackled our problem of fine tuning from the perspective of an engineer. We talked about how an engineer should do something, right? So we talked about how to build a model. Now, in this session, since it's about deployment and performance, we will be taking the stance of an MLOps engineer. So MLOps, if you don't know, stands for machine learning operations. So MLOps covers everything from how the model reaches others, right? So how your model is usable by other people, right? So you build your model in your local machine. Now you want to share your model with others, and that is what MLOps is concerned with. So it's essentially a bunch of cloud, right? So I consider it more inside the domain of cloud than in machine learning, but it's also an integral part. So there are many positions for MLOps engineers as well. So all right, now, this session will be from the perspective of an MLOps engineer, which means we will be thinking in terms of not models, we will be thinking in terms of deployed systems. What are deployed systems? A deployed system will be a system that is available to the public, that the public can use. And so we will be thinking on how do we transition from a model that we have built in our machine, and how do we make it so that it is usable by an entire population of people. So from that perspective we will be approaching this session. All right, so with that, let's go and look at what we will cover today. So we have these 9 points. So just these points are just these points will reinforce what a good system should have, what a good system should be, and what are some good practices you should follow to make a good system. A system being the model turned user facing, right? So now the model is deployed, it's available to all people on the earth, right? On through some means which we will see later on, right? So we will discuss through these 9 points what is important for a good system and what actually makes a good system and how we can create good systems, right? So all right, so is this much clear so far? Just how we will be thinking about our models today and how we will be approaching all this. Was I clear on that front? Okay. Yes, all right. Okay, so let's move on. Okay, good. Now, from the perspective of an ML ops engineer, so first of all, models meet people. So, what do I mean by this? So, uh, when we evaluate a model, so evaluating a model is just getting to know how the model performs, right? So in case of generative models that create new content, we have some metrics which give us some numbers on how the model performs. But now the problem over there is that metrics and input and output that we provide are in a controlled environment, right? So it is inside my collab notebook. It is under my assumptions, whatever assumptions I make. And more often than not, those assumptions are ideal. We test our models through our assumptions in an ideal environment, and we only test prompts that we think are appropriate. So for example, if you have a chatbot for a company, you will test queries related to the company. For example, if I have chatbot for Amazon customer queries, in my controlled environment, I'll ask it questions like, how do I return an order? So what are the steps to return an order? All of that. But in real life, after deployment, a model actually is used by users, people, actual people. And so the users that use the model may not always use the model in ways we intended it. So as we all know, even in chat gpt and all of that, ever since their conception, users have been trying to jailbreak these models, that is, get outputs from them that were not intended by the developer. So the point of this slide is to enforce that models meet people, not our idealized versions of how they should be used, uh, are not what actually they are used for, right? So users are, as it's written in the points, that users are non-cooperative, right? So by default we assume that whoever is using our model is trying to break our system, because that is a good practice, and that is what makes robust systems, right? And inputs are ambiguous, incomplete, or malformed. So we are taking the worst case assumptions that whoever my user is trying to break my model, is maybe not with malice, just out of ignorance, but they are not cooperative with what the model ideally should work with, and inputs are not ideal. So in my controlled environment, I might give the model some hints to create the desired output that I need, right? But if you ask an Amazon customer query model, how do I make pasta, right? That is not cooperative, and that is not a prompt the model is designed to understand, right? And prompts drift over time. What is that? We'll get to that. But what this point means is that our assumptions change. So our input is stationary to the model. After the training is done, we cannot change it. But humans evolve, and so our definitions of classifications also change. We'll get to that point. And when you scale a model on when you deploy a model and scale it on a very large scale, so if you have 1 million users, it is expected that you will hit the worst case scenario in that case, because there's 1 million people using your model. The probability of that kind of behavior is very high, right? So that's what this point means. All right, moving on. Adversarial by accident. This means that when you have such a large user base, it is natural that a small subset of them are use the model in ways that are not intended. So is our system protected against that? It comes back to the first point, right? So users might not want to break the model, but because there are so many of them, it is possible some of them write some prompts that are maybe not malicious, maybe not are trying to deliberately break our models, but just misaligned with what we wanted the model to do. So the example was asking a Amazon customer query chatbot how to make pasta, or who is the president of France, right? All of that is not questions that our model is trained to handle, right? So that happens because users are curious, right? Users want to know what are the limits of a model. Even how we use these language models like Gemini and ChatGPT and all of that, we try to break those models, which try to jailbreak those models. And the responsibility of the developer is to design the model in a way that fits the company's values, right? So whoever we are building the model for. And even if an input is very rare, rare inputs become common at scale. If there are 1 million users using your product, it is natural that out of those million, what you thought was an edge case will be a common case, because that's just how mathematics work. The probability is very high, right? So the bottom line is adversarial in this context does not mean hostile, it means goal misaligned, right? So your model needs to be stress ready to be able to handle all that stress, right? The stress of scale, the stress of user non-cooperation. So those are two stresses, right? And so that leads us to the distinction between what we are doing in our personal computers in collab notebooks, which is an experiment, versus what meets the users, which is a system. So an experiment has controlled inputs and a system has unbounded inputs, right? Anything can be an input. An experiment is reversible, so if we don't like something about the model, we can always retrain it, but that is only until the model has been deployed, because after deployment we cannot change the weights, right? So as an experiment, the mistakes we make are reversible, but in a system it is harder to roll back our mistakes, right? um, and failure is informative in a system, because when we do something wrong, uh, we are able to understand why we did it wrong, right? And we are able to improve and iterate on that in our wherever we are building our models. But once that model is deployed, if we want to make a change, it has some real world costs, right? Because it's now deployed, it's serving users, right? And downtime of the model means your business is losing money, right? And an experiment is optimized for insight and a system is optimized for reliability. That means an experiment tells you what to do, what not to do, what will work, what will not work. But a system should be reliable, right? So even if a million users are using it, it will fail, but it should fail in a way that is predictable, right? So that's how, as ML ops engineers, we should be thinking about our systems, right? How do we transition from a model to a system? All right. So this was the first point, and I hope it's clear. It's mostly conceptual stuff here. I hope I was clear on that front. Okay, all right. So we saw that. Now this is another point, that users see outliers, right? So now we will talk about some problems that we will have when we encounter metrics, versus how do we actually evaluate our model. So metrics are numbers, right? So what exactly those metrics are, we will also get to that later on. But right now we are talking about how our metrics shape how we see our models, and why those metrics can often lead us to thinking something else, right? So the point here is that metrics are a summary of our behavior. So if there are 2 points that are in opposite corners of a line, the metric of mean will give me the middle point, which means that on average the behavior will be in the middle somewhere, right? But that does not mean that when you're dealing with actual users, that the corner behaviors are impossible. Because if we are dealing with a million data points, that means maybe 10 or 20 of them will lie at the corners, which will be behavior that is not desirable by us, right? So users experience single outcomes rather than, those summaries that we create using metrics. And the point here is, the important point over here is that rare failures matter. Why do they matter? Because our customers do not care about, how well you have built the system. If the system fails once, that will be the memory the customer carries of your organization, of your business, for the rest of their lives, right? So you only need to fail once to destroy user trust. So to avoid that, our systems need to be reliable. That is the bottom line, right? Metrics compress variance into central measures. That does not mean those cases do not exist. So a metric will tell you that, there are on average, an average user will be giving a prompt that is safe for the model to handle. But that only means the average user out of a million users. um, of course there will be maybe even 1,000 users that do not fit into a nice mold that give prompts that we desire, right? And when our model fails those users, that will be a breach of trust between the user and the organization. So this is where our models translate into business impact. So that is how, once we have a model and we try to build it into a system, we switch from making a cool fun project into something that needs to be responsible and responsive to our users. All right, so the bottom line here is that systems don't get judged by their mean, they get judged by their worst memorable failure. That is the point, that once you fail, you compromise user trust. All right, so now we have two words here: offline performance is not equal to online reliability. What does offline and online mean? So offline means when your model is not facing the users, and online means once your model is deployed. So those are two states a model can be. It can be offline or online. Offline means your model is not yet deployed, you're still working on it, and it is not taking queries from users. Online means your model is deployed and it has started taking queries from users. So the point here is that if using metrics, if you see some good performance, that does not necessarily mean that once you deploy that model it will give you good results. That is the bottom line here, that metrics will not always tell you what is wrong. You can get zero training loss on your model, but that does not mean your model is perfect. It will still make mistakes once it is deployed, right? So because the point is that all the data sets that we use are curated by us. We make those data sets or we borrow them from somewhere, right? And so those data sets are curated, they fit our ideal version of how a model should behave, right? But in real world, inputs are not always as we desire them to be. They are messy, and the assumptions we make during the building do not hold after deployment because of the sheer size of the user base that we have, right? And as the point is that confidence scales faster than correctness, because you can have a model that is 95% correct, right, but it only works 20% of the time. Or you can have a model that is 85% correct but works 95% of the time. We will prefer the second model even though it is less correct, because it is more reliable. And in real life systems, what matters more over correctness is reliability, right? So your model can fail, but it should be reliable. That is the bottom line, right? A bad test case can be reasoned about, a bad customer experience is lasting, is the bottom line here. So this is all from the perspective, as I said in the starting, we are thinking of from a business perspective, from the perspective of an MLOps engineer, right? So how our model should be facing our users, right? um, all right, so now what if metrics don't actually tell us how the model will perform in a real life scenario? What actually do metrics tell us? So metrics are not guarantees, right? As it's written here, they are not ground truth. But what they do tell us is that in which direction we can improve our model. Because if you get a low, if you are getting high loss, right? That means that something is wrong. Now you can use that metric to move in a direction that makes the model more reliable. So they are navigational markers that you can use to make the model more reliable. They're not perfect figures. So a loss of zero does not mean you have to not work on your model, right? It means that the model is will fail in some other dimension and you need to figure that out, right? So metrics are used as early warning signs, right? And they're proofs of correctness that the model is working, because a loss of zero is so a higher loss means that the model is completely incorrect, right? So lower loss will tell us that the model is correct, but it does not tell us whether the model is reliable, right? Metrics help you notice change. They don't tell you if the change actually matters. All right. That leads us to our next point, which is correctness is not equal to reliability. And we care about reliability more in systems than we care about correctness, right? So correctness can be even in generative tasks, especially, measuring correctness is hard. So because if you ask a language model something and it replies in a particular way, how do you actually judge that what they are saying, what the model is saying is correct? Because if I ask, describe an apple, there are 1,000 ways to describe an apple. Maybe all of them are correct. Maybe they are just framed differently. You can say that an apple is in fruit that is red in color, or you can also say that an apple uh, has a red skin and it is of a spherical shape, right? So both of them are correct. Neither of them is more correct than the other. So that is why we say that correctness is not equal to reliability. Your model can be correct, but if it does not work reliably for a majority of the time, then it's useless, right? So as it said, that correctness is for individual outputs and reliability is behavior over time. So your model works for one input, good, the output is correct, maybe it's correct, right? But for a million users, is it working reliably on every single one of them? That is what we want to know, right? That is reliability, right? Users don't need perfection, they need predictability, because once a user knows that your model behaves a certain way, they will engineer their inputs to fit that way. All right. So far, I think I've said nothing too outrageous. Is it clear so far? Because it's all just a bunch of theory, right? To set the ground. Am I clear so far? Okay. Okay, it says it's clear. All right. Okay, good. Okay, all right. So let's move on. So the next point is that failure should be predictable. Now we need to understand that our models will fail at some point in time. That is inevitable, because that's just how, that's the nature of technology, right? Failure is inevitable, but how you deal with that failure as an MLOps engineer is important, right? So the best kind of failure is predictable failure, where you can predict that my model will fail on this particular input, and this is how I will deal with it. So it's actually all about having a plan. Once you have a plan, you can deal with failure. So if you know the boundaries of your model and how it will fail, you can actually plan ahead. But if you don't know the boundaries of your model, if you don't do your due diligence, the model will fail randomly, which will cause, user trust to go down, which will in turn cause your revenue, your organization's revenue to go down, right? So, right. So as the point says, all models fail, and unpredictable failure is what erodes trust. So your failures need to be predictable for the users to trust you. And evaluation maps failure boundaries. So once we evaluate our model, and this is why evaluation is important, because evaluation is about knowing the limits of your model and how it performs and how reliable it is. So once we perform evaluation, it tells us that you know that the model has these boundaries and this is what the model can handle, and that sets us up for predictable failures, right? So the bottom line here is that users observe behavior, right? So if I know that ChatGPT fails on this certain input, I will try to model my future inputs so that the model does not fail, because that is how humans work, right? But if I know for sure that the model will fail on this particular input every time, that is reliability, that is predictable failure. If I'm just using my model casually and it fails, that is unpredictable failure, which is bad, because that will erode my users trust in the organization, right? So the bottom line here, as it's written, is a good model teaches you how not to use it. All right. Now we will look at a case study of when on paper the metrics are fine, um, but when deployed, uh, things did not work out as they thought, right? So I have two case studies ready, and we will try to understand what's going on and what actually failed in the system, right? So the first case study is about Amazon, right? So Amazon built a system, right, that automatically ranks resumes, right? So a machine learning model that takes in a bunch of resumes and tell us that these are the ideal candidates for the job description, right? So the input was resume text and the output was a ranking for the candidate, right? And they trained the model on a bunch of historical data. So far so good, right? And the offline metrics, when the model was not deployed, they saw that the model was pretty accurate, so it had high agreement with the historical outcomes, right? And the accuracy was also pretty good on validation data, and the performance was stable. So they observed these three things during offline testing. Now why this is important is because it tells you that even though the metrics indicated that everything was good, it did not work out as well, right? Because even though the agreement with historical outcomes was pretty good, the accuracy was pretty strong, and the performance was stable, they ran into an issue that the system would not consider female candidates for its positions. And why was that the case? That was the case because historically, in the data set that Amazon took, historically, um, there have been these technical positions have been dominated by men. So the model learned to bias itself towards male candidates, right? So whenever it saw terms relating to female, it automatically penalized the resume and gave it a lower rank as compared to a male, right? So as it's written here, the model systematically penalized resumes associated with women. So if you had written something like women's chess club, or women's society or something, right, the model would not consider your resume, and it would in fact penalize it and keep it down. So that was a system failure that was not seen during evaluation phase, that slipped by evaluation phase, even though the metrics indicated that it was all fine. But in deployment, Amazon realized that something was wrong, right? So this happened because the historical data was encoded in such a manner that it biased towards men, right? And so the metric they were optimizing for is was to match historical decisions, not to hire fairly. So that is also a distinction between the values they were aiming for. Their value should have been to hire candidates that are the best fit for the job. But during the offline development phase, what they optimized for instead was to match the historical data. uh, and so the model was correct in a technical sense, but it was wrong because it did not align with the values that the company was going for. And that is an example of where metrics can fool you. So we have to be very receptive of how we treat our metrics, and we have to handle them with care, because metrics don't always tell the entire story, right? So that is the first case study. So this was Amazon. And we have another case study about Zillow, right? So what Zillow did, Zillow used ML models to predict house prices, and not only that, it also automatically bought those houses. So this feature, they introduced a feature called iBuying, which automatically bought houses on predicted home prices by some ML model, right? So now the problem over here is, the first problem over here is that they have directly linked the ML model to a financial aspect, right? It is directly linked to capital, because not only is the model predicting, it is also doing the buying. So that means there is capital involved. Now this can go horribly wrong in a number of ways, right? So the offline metric suggested that it was fine. Why? Because uh, Zestimate dealt are dealt in this trade in historically they dealt this trade, right? So they had strong predictive measures in history, and while testing, they saw very small margin errors. So, of course, in this case as well, everything seems fine when the model is not deployed. But what went wrong here was that the input is stationary, right? The input to the model is stationary, it is historical data. But the world we live in is not stationary. House prices evolve every single minute. By the second, they evolve, right? So the input data was stationary, but the data the model is operating on is not stationary. It changes rapidly, right? Because it's the housing market, right? So the assumptions the model had taken from the input data will not hold if the data itself changes, if the housing market changes, right? So this led to errors. So maybe in 1 year the housing market did not change as much, but over time, in 1 year, 2 year, 3 years, uh, the errors compound, right? So there are multiple small errors, and those multiple small errors compounded to form a very large loss of billions of dollars in losses, right? So the outcome was that this whole program was shut down by Zillow. iBuying program was shut down, right? And as a consequence of that, one fourth of their workers were also laid off. So somebody had to suffer the consequences as well, right? And there were billions of dollars in losses. So with this case study as well, the takeaway here is that metrics don't always provide a perfect picture of the ground reality, and we cannot know what the ground reality is unless we deploy a model and have fail safes in place. So the problem with Amazon was that their training goal was misaligned. They were optimizing for matches that fit historical data instead of matches that were optimal for the job position, right? And in case of Zillow, the problem here was that the data that they trained on was stationary, whereas the data that the model will operate on after deployment was not. So that led to compounding of losses. So I hope this is clear. There are these case studies, so I don't think there is anything intellectually challenging here. Is it clear? These two case studies that we studied. All right. Anubhav says yes, it's clear. All right. Let me check the Discord real quick. Okay, no one's here. Okay, all right. So now that this is clear, these two case studies are clear, we can move on, right? So that leads us to our next point, which is that evaluation is not a single step, it is actually a process. At every step of your ML pipeline, you should be doing evaluation, right? Before training, you should be evaluating. So at each step, evaluation tells us something different. Before training, we evaluate a model to establish a baseline that this is how the model performs before fine tuning, and after fine tuning we will perform evaluation again to know that this is how the model performs after fine tuning. So evaluation is a process, a multi-step process that comes with every step of the pipeline, right? So during training, to catch overfitting, that the model is overfitting on the training data, to catch that we will do evaluation, right? Using loss. After training, to measure the task behavior, we will also perform evaluation. And even after deployment, we keep performing evaluation, especially in big corporations. It's about constant monitoring and auditing of whatever systems they have built, right? Because a good system is a continuous process, not just one and done, right? After deployment as well, to detect drift and regressions and all of that, we need to continue our evaluation process, right? Evaluation at each stage checks as a sanity check for whether the model still aligns with our end goal. So that's the bottom line here. All right. So right. So now we will talk about some metrics, some common metrics. So now we will actually talk about some metrics that we can use for evaluating our models, right? So metrics give us a signal, as I said previously, on which direction we should proceed in to improve our model, right? Metrics define the next steps in the process, right? So metrics are instruments to navigate the change in our systems. All right. So now there's a distinction here. So for classical ML tasks, machine learning tasks like classification, there was a very set output, right? There was a ground truth that, and it was absolute, that this is the perfect output. So classification model asks that, is this picture a cat or a dog? And the output is either a cat or a dog, definitively, right? There is no question about that. So the output is absolute, right? We have a hard label, there is a single truth. But in case of generative models, there can be multiple outputs, and all of those outputs can be equally correct, right? So that means, how do we evaluate our generative models, right? How do we evaluate those models? Because as I said earlier, you can ask the same question and get two different outputs from language models, and both of them are correct. Neither one of them is wrong, right? So how do you evaluate those things, right? So the in generative models there is no single truth, right? The only real baseline we can use is the output useful to us, right? Okay, and so there are two words here: closed output spaces and open output spaces. Closed output means, of course, in classical ML tasks, that the output is closed. There is one single output, one hard output, or maybe two to three or n, but a specified amount of correct outputs. Whereas in open output spaces, there are, maybe infinite outputs, and all of them are correct, right? Just changing the word order or changing the phrasing, right, in generative tasks. So that's where evaluation of generative models using numerical metrics differs from classical tasks. All right. So we have a few metrics here. So to evaluate our machine learning, so to evaluate our generative models, we use these metrics. So we have accuracy, we have blue and row, which are the most commonly used, and we also have perplexity, right? So These three are useful as metrics, as I was saying, but they need to be used with caution, as we saw earlier in our case studies, that they are only guides, right? So, what do these mean? So, what is blue and BLEW and rogue, right? So, these two, blue and rogue, are discuss surface similarity. So, what do I mean by that? I mean that when I say that they measure surface similarities, that they measure how much of the words in an output are occurring in what the user wants the output to be. So by that I mean, by that we mean that, so let's say I ask a model, uh, describe an apple, and it gives me some output, right? An apple is is a fruit that is red in color and whatever, right? And I have prepared my own answer for that, which I take as the gold standard, that this is what the output should be, right? And what blue and rogue do is that they check the similarity of the words. So, are all the words being used that are in the preferred output, are they being used in the output generated by the model? So, for example, my preferred output might be something like an apple is a fruit that is red in color and spherical in shape, right? So, what blue and rogue do is that they check word similarity. So, is apple occurring in the output of the model because it's occurring in the output I desire? Is apple is a fruit, is the word fruit occurring in the output of the model because it's occurring in the gold standard answer, right? And so it evaluates surface similarity, right? And there can be, single word comparison, so word to word, is apple occurring? There can be two word comparison, so is apple is occurring in the same sequence? So there are actually called n grams, right? So we take n words at once, and we check, are those n words in the same sequence occurring in the output of the model as they are in the gold standard, in the preferred output, right? So that's how blue and rogue work, right? Accuracy, as we all know, is a measure of label agreement, right? So in some tasks, so if I ask what is the capital of France, the answer is, of course, Paris. There might be some fluff around it in case of generative model, but the answer is Paris. So that's a clear label distinction, that it's either Paris, the model is output given me Paris, or there is no Paris in the output, which means the answer is wrong, right? So that's accuracy. And what is perplexity? Perplexity is a measure of, it measures how surprised our model is with the data, right? So it measures the fluency of our model's output, right? So so those are three measures that are used. So I hope these three measures are clear. So I'll just real quick ask, and if you have any doubt, you can ask right now, in any of the previous slides or this slide. Yeah, if you have a doubt, you can ask. And over at Discord, okay. Okay, all right. Then I hope that everything is clear so far, right? Okay, all right. So let's move on to the next slide, which is that, so these three metrics that we just studied are metrics that are model centric. Now let's talk about behavior centric metrics, right? So these evaluate behavior instead of, how well the model is performing. So these are more general metrics that we can use. So how consistent is our model over time? And these are evaluated by human beings, right? So what is the failure rate per user per session, right? So if you have a million users, out of those, how many fail, right, in per session, right? So that's the failure rate per user per session, right? The output variance under small input perturbation. So this just means that how widely our output varies if I make a small change to my input. So these are behavior centric metrics that we can also use to evaluate our models, right? And these are what determine reliability of the model. All right. So now we assume that we have deployed our model, right? So there are some other metrics that after deployment we need to focus on, and those metrics are data drift, concept drift, and proxy drift. So let's say you deployed a model that predicts house prices, right? So there can be three types of drifts that affect the performance of your model. So the first is that inputs like user language evolve. So over time, the way we speak, the semantics of that evolves. So the data the model was trained on might be different than what it is encountering, 1 year down the line. So that leads to a drift, right, in the data. As we discussed, that house pricing may not remain consistent, right? So that is known as a data drift, right? There are other types of drifts. The second is concept drift, which means that the semantics of predictions evolve. This means that what we are actually trying to predict with the model, what we are actually trying to generate with the model, evolves over time. Like in the case of Amazon, what they were trying to predict was the optimal candidate, but they ended up predicting something that was uh, not what they intended to do. So that is known as a concept drift, right? That when what we are trying to predict changes over time. So these happen over time. That's why it's called a drift. It slowly changes over time. So data drift happen when inputs to the model evolve over time. So they do not remain same over the years. Semantics evolve of what we are trying to predict with the model. That is known as a concept drift. So at one point of time, the aim was to predict house prices, but over time the aim evolved, right? So that is a concept drift, and a proxy drift is when the outcomes of the model evolve, right? So these are three types of drift, and these are post deployment metrics, and these are known as post deployment metrics because these occur after the model has been deployed. So there's data drift, there's concept drift, and there's proxy drift, right? And the line here is that humans are not stationary creatures. We evolve rapidly, and therefore a good system evolves alongside to retain usefulness. So to make sure that a system even after deployment is useful, we need to evolve a system, right? So that's about that. Now we move on to the next point. Now we move on to deployment. So how do we actually deploy our model? So there are four major ways you can deploy your model. So to deploy a fine-tuned model, we have four ways. So the first is API-based deployment. The second is cloud managed deployment. The third is on-device, also known as edge deployment, and the last is batch or offline deployment. Right. So what are these four ways? Let's discuss the four ways of deployment. So the first is API-based deployment, and this is very common. This is what we mostly use, right? And even as students, you will be using this method the most, right? So what is API based deployment? So does anyone know what an API is? Real quick, just a knowledge check. Does anyone know what an API is?
Application programming interface.
Yes, correct. So an API, as Anubhav said, API is application programming interface. So an API based deployment means that we use an API to reveal the model to our users. So how this works is that if you have done a bit of web development, you will know that an API takes requests from the users and it gives an output. So how API based deployment works is that we have our model ready on somewhere, and we have an API in front of it. So a user can request some output. So the user will send me a request that this is the input, use your model and give me an output. And so there is a layer of API between the model and the end user, right? So the model runs on the server. Clients send requests using a protocol, which is mostly HTTPS nowadays, right? And the server returns the predictions. So the user is not directly interacting with the model. The user is interacting with an application programming interface, an API, and that API connects the user with the model, and they share outputs, right? So this is how it's usually done. You will have the model hosted on the server. The server will have an API in front of it, which the user will query, and then the API will ask the model to generate an output, and then the model will return the output to the API, and then the API will again tell the user the output, the prediction, or whatever we are trying to do here, right? So in Python we use you would use something like Flask, Fast API, or Flask, or Django, right? In JavaScript also you can make your own APIs, right? You would use something like Express.js, but the point here is you will have your model hosted somewhere. So in case as students, you might have the model on your own personal computer. If you're using a cloud hosting service, you might have your model there, but then you have to get integrated with their environment, right? And so yeah, you can use fast API Flask, or you can actually also use services like TorchServe and TensorFlow serving, right? So these are these are by Google, right? You can use, and you can also use Docker. If you know how to use it, you can also use Docker for packaging your ML model. All right, so these are best for web applications, mobile applications, and multiple users. So why are they good for web applications and mobile apps? Is for the simple reason is that you do not, models are actually very large if you want to train a good model. So as we know, models are like gigabytes of space, and you do not have that kind of space to work with in web applications and mobile apps, right? In web, we can only access the cache of the browser, right? And in mobile apps, the storage is around like 256 gigabytes at maximum, so we do not have a lot of space to work with. So what we do is we offload the model to somewhere else, right, on some cloud, on some server, and then we make request from the device, which will be a mobile device or whatever, from the web app, and then we get the output. So that's why it's good for that, and it's also good for multiple users, because that's the nature of web development. It's often good for multiple users, right? Because of various constructs in web development, right? Next, another type of deployment that you can use is cloud deployment. So here you are entirely engraved in the cloud infrastructure, right? So you can use a cloud deployer, which will they do all the work for you. So you can use AWS SageMaker, Google Vertex CI, which is what our course is concerned with, and you can use something like Azure machine learning, or some other platforms, right? So all these platforms, they host the model for you, so you do all your machine learning work in the environment provided by these platforms. So as we saw in last session, for fine tuning Gemini, right? We did that inside Google Cloud Platform, and so from there only I can host the model. So that's very convenient, but that also restricts you to that environment where you are, right? Um, so there are some pros here, that auto scaling, because the infrastructure for the model, all the hosting infrastructure is managed by the service you use. So in case of Google, Google will manage all the infrastructure, all the resources you need. Amazon will manage in case of AWS, right? And a lot of things there are automated, so a lot of monitoring, a lot of auditing that you will have to perform manually if you deploy your model manually will be done automatically in case if you use a cloud service provider such as Google or AWS or Azure, right? And a lot of logging, so how many users use your model, at what timestamp they used your model, what was their specific request, all of that. So a lot of that is automated in these services, so they are very convenient. And a lot of large organizations use these hosting platforms. But um, right, and the last point is less operations work, so your workload is cut because of a lot of automation on these platforms, right? The cons is that it comes at a cost, right? So they have a cost, it's not free, and as students you might want to avoid that. So uh, your alternative would be something like API based, or you can also actually there are some free cloud services where you can actually deploy your models as well, right? You can use something like so for web apps we generally use something like Vercel or Heroku or Render, all of those, right? So free alternatives you can find as students. Um, but to actually host something permanently on cloud, it's expensive over time, right? uh, Not expensive, but it has a cost over time. And vendor lock-in means is that once you're integrated into, let's say you chose Azure ML, once you're integrated in that Azure ML environment, it is hard to switch because now you're locked in with that vendor. And that's what this means. Okay, all right. Another way you can host your model is on-device deployment. So this means that the models runs locally. So this means that if I train a model, what I do is I send a copy of that model to all the users. So if I want to share my model with you, I'll just send the model along with the application packaged inside to you. Now that is good for some cases and bad for some other cases. As we discussed, sometimes models can be gigabytes in size. So for devices that are low on storage, you might not want to do this approach, right? You might not want to send the entire model with your application, so that will make your bloat your application to like hundreds of gigabytes, and nobody is going to download your application, right? But in some cases, when your model is relatively small, it is better to just package the model with the application and send it as one single package. So this is why it's called on device, because the end user device, the client device, is gonna be the one that's going to do all the compute, right? um, so for example, Google ML Kit in Android, you can use models from that. uh, they are locally run, right? So you can use models like that. And there are desktop system and embedded systems also do this, right? So there are some techniques we can use to actually um, decrease the size of the model, and those techniques are something like model quantization. So what does model quantization means is that usually when we make our model, when we train our model, the weights are calculated. So all the calculation, all the mathematics is done in 16 bits of precision, 16 bits of floating point precision, right? So that means you need 16 bits to store numerical values, right? So what you can do actually is, after you have done your training process, you can decrease the precision from 16 bit to something like 8 bits or 4 bits. So that means, to represent a number, instead of using 16 bits, now your model is only using something like 8 bits, which is half the size of your model previously, right? So that also decreases the size of your model. So that's known as model quantization, and many models and many systems use these kind of techniques to decrease the size of their model. There is also 4-bit quantization, but you lose a bit of precision every time you quantize your model. So you have to consider the cases where you want to actually do this, right? You can also use some conversion, like ONNX is widely used in TensorFlow, Core ML, TensorRT, all of these you can use. And you can also just switch out your model for a smaller one, right? Just use a smaller model. So this is best for when you, so this is a big advantage. Why might you want to do on device deployment? Because once your model is on the device of the end user, they can actually just use it offline. They do not need to be connected to the internet, because the model is on them. In case of cloud and in case of API based, in both the cases, the user, the end device, needs to be connected to the internet to send an API request or to query the cloud, right? But in this case, yeah, since everything is completely offline, you can actually just do that, right? And it is also privacy sensitive data. So in cases where your data is sensitive, you might want to, not share it with the provider, right? So in case of if you're doing something sensitive, in case of military or high frequency trading firms and all of that, you might not want to query connect to the internet in those systems to avoid attacks, right, on your system. So you can just do this. So that's a big advantage of on device deployment. Okay, all right. Now we have another type of deployment, which is known as batch deployment. So what batch deployment actually is? So batch deployment is that the model runs on, so some models might receive bulk requests, so a lot of requests at a time, so hundreds of thousands of requests. So how so for those kind of models, we can do something like batch deployment, which means the model runs on scheduled jobs instead of real-time requests. So the above three architectures that we looked at, they responded to real-time requests. So user requests, the model instantly processes it, and it responds instantly. So the idea for batch deployment is that instead of answering the user upfront, we actually wait. We hold out, we take a bunch of requests, we process all of them, and then we answer the user at some point of time, right? So the example here is nightly prediction. So over the course of a day, you take all the user queries, you process them at night, and then you send them out, right? Data pipelines also use this kind of deployment, because they're not user facing. Maybe it's an internal pipeline in an organization, so it does not need to respond immediately, but so it can do that. And analytics workflows also use this, right? So you can do this using cron jobs in even Node.js and JavaScript. You can use Airflow, right? And this is also a feature in cloud. So cloud is all encompassing, all right? So yeah, so that's the types of deployments we can use. Is that clear to all of you? Am I clear on the types of deployment? Or if you have any doubt, you can ask me. Okay, all right. So I can also actually show you this here. Let me just share something. All right. So what I'm showing you right now is this is a project I made in the past for a hackathon, and this actually is an example of what you would call on-device deployment, because here the model is not querying somewhere else. The model is on the device, and I use that model to answer queries. And so this is also a project for answering user queries, right? So this is also a machine learning project. So if I just run this, so here, as you can see, it has a simple interface. Now the point here is that, okay, already it's not sharing. So, this is a simple, project that you can see that you just enter a query and it answers the query. So this is a language model. So this is to answer user commerce queries, right? So this is an example of on-device deployment, because in this project, what I did was that, so this is in Python. So what I did was that the model is on the device. It is on Olama, which is a software that can host models locally. So this is an example of that. And so what this does is that it queries the model locally and it responds to the queries locally. So uh, a good thing about this will be about privacy, that all the data is within the system, so it's not going anywhere, and it can run offline. It can run 100% offline, which is rare for language models. But the downside is that it is very slow, right? So the queries will be answered very slowly. So that's a downside for this. So all right, so that was one example. um, Let me get back to the slides here. Okay, all right. So we talked about how we deploy our models and the types of deployments we can use. So now this is a section on, once you deploy that, how do you handle failure, responsibility, and trust, right? So as we talked about earlier, so users work on trust, right? So a user will not remember the model's best performance. The user will remember the model's first performance, right? So once your model is a system after deployment, it now faces users, right? And we discussed that failure is imminent, right? So what we need to be prepared about is that we need to be prepared for that failure, and we need to handle that failure gracefully in MLOps, so that we can retain our user base, right? So the thing at stake here is customer trust. So we do not want to lose our users, right? And so you need to be ready as an engineer to design your system in a way that handles all of that, right? Because the thing at stake here is user trust. All right. So what is negotiable failure? Negotiable failure is when the failure comes at your terms. So since a failure is inevitable, why don't we design the systems in a way that bound those failures, right? So we can use a variety of techniques to do that, which we will see, right? So as it's written here, we can actually bound the failures of our system within desirable confines. So we can actually just know when our system will fail and be prepared for that, instead of having to deal with failure that we have not prepared for, right? So a random failure is something that appears arbitrarily, breaks user mental model, and destroys trust. But a predictable failure is something that has clear boundaries and has consistent refusal modes and stable degradation. So that means that's predictable behavior, which comes back to the main point that our model needs to be predictable and reliable. As it's written here, the bottom line is a good model teaches you how not to use it. All right. So that leads us to some techniques we can use in case of a failure, right? So after deployment, there are multiple techniques we use to make our systems more reliable, right? So the effect of a failure can be mitigated by using these techniques, which are version deployment. So what does deployment means? Version deployment means that once you complete your code, you deploy it in terms of versions. So I have app version 1.0, which has all the base features. Then I can keep working on my app, but not release it, right? I can just keep working on my app, and once some set of features is done, I can release those features as another version 1.1 of my app. So that's called version deployment. And if something goes wrong in version 1.1, I can simply remove that version, and we can all go back to version 1.0, the stable version. So that's a technique that we use, right? And similar to that, we have something called instant rollback. So instant rollback means that once something goes wrong, we move back in time to a stable version, right? So in cases like banks have this. So if your transaction somehow goes wrong, you will get your money back, because the bank has a save file of sorts of before the transaction, right? So the bank rollbacks to that state of your account. And we have something also called rate limiting. So rate limiting is something to protect us against DOS attacks, right? Denial of service attacks. So a user cannot keep requesting instantly. So per second, they cannot send 1,000 requests. Maybe you want to limit the model to only process 10 requests at a time. So that's called rate limiting, right? Incident logging is also another feature. That is, whenever something happens, a query occurs or anything occurs, uh, we maintain a log, right? So that's called incident logging. And a lot of these features are automated using cloud deployment. All right. So that was my section for model performance and deployment. So if you have any doubts, you can ask them right now. If anyone wants to ask anything, they can ask right now. That was all about model deployment and evaluation. So what we learned today was that first of all, reliability is more important than correctness. We also learned that users will facing our system will remember the worst failures, not the times it worked perfectly. What we also learned was that metrics are a good navigational tool to tell us where we need to head and in what terms we need to improve our model, but not an end goal. In the end, we have to do some human, user senses to evaluate our models, right? And so we also learn the types of metrics we use. So in case of classical ML, and why those fail in generative machine learning. And we learn what are the, what is accuracy, what is blue, what is row, and we learned all of that, what is perplexity, all of that, right? And so we also learned how our systems can fail due to things like data drift or concept drift, or proxy drift, all of those things, right? So we learned about all of that. And then we talked about how we can deploy our models using the four architectures that we have, right? So API based, we can use Flask or Fast API, or we can use cloud managed deployments, which use, cloud instances of AWS and GCP and Azure, all of that. Or we can do on device deployment, which means send a copy of our model to the device that we are using it on, right? And so all of that. And we also talked about how we can, that failure is inevitable, and how we can deal with it, using some techniques that we have. Okay, all right, so that's all from my side. If you have to ask anything right now, you can ask it. Okay, it seems like everything is clear. Okay, good. So I guess I think we should move on to the closing thoughts. So here, I hope that all of you have learned something over the past 4 weeks that we have been doing these sessions, right? So the initial plan was of 3 weeks, but uh, everything was not being covered appropriately in those 3 weeks. And I still think that the allotted time is a bit small, but we have to make do in what time we have. But the hope is that all of you have learned at least something about fine tuning, and how you can actually fine tune and make your own models. So you have actually gained something from this session. And um, what I think is that if you have learned something, then that's awesome, and you should apply those learnings and actually make projects with them. And because knowledge is only as good as it is used, as it is applicable, right? So the hope is that whatever you have learned, you can apply that. And if you have any problems in applying that, I'm always there. You can just ask me, ping me on Discord, right? But the main point is that you have learned something in these 4 weeks, and you can actually apply those techniques, and you can say that you actually understand fine tuning, because we did a deep dive into what fine tuning is. We covered a lot of technical concepts, right? So what it's supposed to be, what actually happens in the architecture of the transformer when once we fine tune. So we did a very big deep dive on that topic, and so the hope is that you learn something. And if you have learned anything, then my job has been fulfilled. So what I was here to do has been fulfilled. All right. So those are my closing thoughts. And of course, thank you to all of you, those who have attended over these 4 weeks. The um, attendance has been pretty consistent. Of course, there has been a bit of drop off from the start, but we have averaged around 10 people for every meeting, so that's awesome. Having such an attendance is also good to retain, even 10 people throughout the course is very good for me, right? For us, all of us. And so, yeah, that's my closing thoughts. But before you all leave, I would like you to fill this feedback form, so that we can have your feedback, and we can actually improve our future events. So all of you are requested to please fill this feedback form. Just scan it. I think we will also share this with you, right? But just scan it and fill the feedback form, so that we can know how we can improve our future events, right? So please, all of you, scan this. And of course, thank you to all of you who have attended these classes, right? So a lot of you have been recurring. So Hokesh has been there from the start. I also recognize Sarthak. Anubhav has been there, right? And Roshan was also there. I think he did not attend one session, but other than that, he was there. Manav, I think, has been here for like 2 sessions. Ashleen is a relatively new name, but I think she was also there in the first and second sessions, right? So a lot of people, and a lot of with a lot of consistency. So I appreciate all of you for that. So just scan this feedback form and fill it. And if you have to ask anything, the floor is open for all of you. So if anything. Okay. Thank you for session. You're welcome, Hokesh. Thank you for attending. Okay, Naman has prepared that message as well. Okay, all right. Yeah, that point as well. That by the end of January or before, we will announce the top performance, right? Anubhav says it was a nice session. Thank you, Anubhav. Thank you for that praise. Right? Yeah, all session recordings will be going to YouTube now. All right. Okay, all right. I hope all of you have filled this feedback form, and um, anything else, if anyone wants to say, you can still say. Otherwise, I think we should proceed to conclude our session. Okay, then, all right. Okay, guys, thank you for attending, and I'll see you in the next event, whatever we have in store for all of you. Just stay tuned for GDG events. All right. Okay, thank you, all of you. Bye.